Hi, I'm Fernando Pereira from the Federal University of Minas Gerais, and today we conclude our class about the implementation of worklist-based algorithms to solve constraint systems. We will see a few more ways to speed that algorithm up. We start with the notion of strong components. A strongly connected component, a strong component for short, is a connected subgraph in a graph. For instance, in this example, which we have used in the last class, we have four strongly connected components. From this notion of strong components, we can define the reduced graph, GR, I will call it, of a graph. GR is the graph that we obtain by replacing the strong components of G, the graph, by single nodes. The nice thing about the reduced graph is that we can sort it out topologically. This graph is always acyclic. Can you see why that's the case? So, given a dependence graph, which might have cycles, we can extract its strong components, and then we can build the reduced graph. And why am I talking about this reduced graph at all? How can we use this notion of a reduced graph to speed up constraint solving? We can again rely on topological ordering. We can solve a mini data flow analysis per strong component in topological order. Remember, the reduced graph is acyclic. The thing is that after we solve a strong component in topological order, we will never have to revisit. All its dependencies have already been sorted out. This is a very important property. This thing with never having to revisit a solved strong component, I wish you could think for a moment about this property. You can even stop the video to think about it. Can you make sure that you agree that you will never visit again the constraints in a strongly connected component once you solve it if you visit the components in the topological order of the reduced graph? The only way that the information related to constraints can change is if their dependencies change. Does that make sense to you? For instance, in this example of ours, x1 is the only constraint that adds new information to the component formed by x2 and x3. If we know that x1 will not change anymore, then x2 and x3 can only change due to each other. They cannot receive external influence of any other constraint. Let's see how we can rely on strong components to speed up the worklist algorithm. We start with the component that contains x1 only. That's a singleton. Once we solve x1, we will never have to worry about it again. It has no dependencies. After that, we move on to the component that contains x2 and x3. We will have to iterate a bit within this component, but notice that iterations happen only due to dependencies between x2 and x3 themselves and involve only these two constraints. No external information causes us to iterate, and eventually the system stabilizes, the system formed by two constraints. And we can move on to the next strong component. In this case, the next component is the one formed by x4 and x5. Again, we iterate a bit within this component until we reach a fixed state. After that, we move on to the last component, which is a singleton. It contains only x6. That's only one constraint, and we already know all the incoming information because we have solved the previous components already. So we solve x6 in a single iteration, and that's it, we're done. About these iterations within the same component. They can happen in any ordering, We can implement them in a round-robin fashion, for instance. We can even use round-robin in the entire constraint system, involving all the constraints in all the strong components. That would simplify things, actually. The drawback is that we might have to iterate more if we apply round-robin on the entire constraint system. Anyways, here's the pseudocode of a round-robin iterator. It simply goes over all the constraints, solving them in order. In practice, we do not have many more iterations than if we were using strong components and reverse post-ordering if we apply this on the entire constraint system. However, the best is to save round-robin just for the constraints within the same strong component. For instance, let me show you what we get if we solved the entire system of constraints using round-robin. We start with all the sets empty, or rather with no information. That's what the inverted T means. Do you remember that? We can go over the constraints once. Notice that I'm simply evaluating them one by one in the order they appear. We could use some nice ordering like reverse post order, for instance. But that's not really necessary for correctness. It would be good for speed, though. But in this example, we are already using reverse post ordering. And in a second iteration over the constraint system, we are done. See, in this example, we could solve all the constraints in just 2 iterations if we traverse them in round-robin. The second iteration is there just to make sure that nothing had changed. The second iteration creates no new information. One last thing that I would like to discuss in this class before we are done is about how we represent these in and out sets. Do you remember? All the constraints are filling up sets. I mean, we have a system of equations that range on sets. Usually we think about equations as producing numbers. But here we are talking about equations that produce sets. Those are the in and out sets from before. If you remember, our running example would consist of a constraint system with 12 sets. We had 6 in and 6 out sets. You can see them in this picture that shows the 6 program points that we had. The implementation of these sets is very important because we need to add new elements all the time or remove elements depending on the analysis. Furthermore, we need to do union of sets all the time too, or intersection again depending on the analysis. For reaching definitions, we need to add elements and we need to perform a union of sets. So can you think about a nice implementation of these sets? I'm leaving some questions for you here. Perhaps that's a good time to stop the video and then answer these questions. Try to answer them yourself. There are many possible implementations of sets. We can use linked lists and hash tables, for instance. But many compilers implement these sets as bit vectors. In a bit vector, we assign numbers to each possible element that can be part of a set. And then we can set bits in the bit vector, meaning that the element is present in the set. Let's see how we could represent reaching definitions using this idea. So here you have the implementation of sets as bit vectors. We have only 6 program points and each definition is associated with one of them. Therefore, we would have 12 sets, 6 in and 6 out sets. So our bit vectors need to have at most 6 positions because we have 6 program points where information can be defined. And we can access elements in constant time in a bit vector. Union or intersection is also fast, but that's linear on the number of bits necessary to represent the elements in the set. And that concludes this class on worklist algorithms. That's a pretty old technique, worklist in the implementation of compilers. I've left some references for you in this figure in case you want to know a bit about the history behind these ideas that we saw in this class.